How's everyone doing today? That's good to hear. I'm doing pretty fine myself. Was rudely woken up like an hour and a half early. But that also means I had time to get everything done early and to go to Duck Donuts. So I can't complain too much. Alrighty. Okay. So today we're gonna finish up talking about 14.7 optimization. So we talked about finding, yes, shoot, what's up? So exam 2 is going to cover, so everything, so since the last exam, so basically chapter 14. So let me, hang on. So yeah, exam 1 we ended with, ended chapter 13. So exam 2 is going to cover basically all of chapter 14. So starting with functions of several variables, 14.1. So limits, continuity, partial derivatives, tangent planes, gradient directional derivatives, chain rules. What we're talking about today, optimization, and then Lagrange multipliers, which we're talking about tomorrow and Friday, which is just another way of optimizing functions. But yeah, it's gonna cover everything since the last exam through what we're talking about on Friday. Exam 2 is going to be next week again. So yeah, it's going to be on a Tuesday next week. So Monday is going to be another review session. So we're going to finish up talking about Lagrange multipliers. We're going to do that tomorrow on Friday. Monday is going to be a review session. We'll do the same thing. I'll probably have a review, just a long review in place of office hours, and then I'll have office hours later in the day, like we did last time. Yeah.
Will there still be, you know how you uploaded like a practice worksheet on Canvas, the ones that you wanted us to focus on?
Yes.
Will that be uploaded? Is that uploaded yet, or?
It is not. I have not received it yet, I believe. Let me actually check. I haven't checked this morning, so perhaps.
Yeah, because if not, like you said, there's those exams on the math, the Penn State math website. So
yeah, those are still always good to look at. In the meantime, but I suspect we'll get some soonish. Probably by like Friday, something like that. I can't say for sure, but whenever the course coordinator provides us with those. But he's been pretty good about it so far. So yeah. Okay.
The only thing I would say is if we have like if we get those problems again, like the ones that you said to focus on that you post on Canvas, like not the ones on the math website, if like you could maybe give us like a couple of steps on like how you solved it, because last time we kind of just had like the answers and some of them like I didn't know how to do.
Okay, I will. I'll go ahead and write up solutions for those. I was sort of expecting like solutions rather than just the answers, but that didn't happen, and I waited a while to get those. So as soon as we get them, I'll just write up solutions for you guys. Shouldn't take too long. Yeah.
Thank you.
I'll do that this time. Yep. Alrighty. Excuse me. Okay, so last time we looked at finding the local extreme values of a function. So local maxes and local mins. And that means basically if you just look close to a local max or min. So a local max, you look close to the local max, close to the point AB, the function is going to be less than or equal to what it is at AB everywhere nearby. So they're going to look like little hills, basically, and little valleys for local mins. And we saw those happen at critical points. We did a second derivative test to determine whether a given critical point was a local min, a local max, or neither, in which case it's a saddle point. And that's what we did last time. So this time we're going to look at absolute extreme values of a function. Hang on, let me. So this is optimization continued. Okay. So we're going to look at absolute, or also referred to as global extreme values, or global extrema. So extreme is just a plural of extremum, and an extremum is a max or a min of a function. Okay, so we saw, so for instance, for functions of one variable, local maxes and local mins can happen. So those happen at critical points where your derivative is 0. But a given local max or local min doesn't have to be an absolute max or min. Suppose we go from, say, from A to B. So for instance, this guy up here is a local max, and it's also the largest value of the function anywhere. It's the highest point on the graph from x equals a to x equals b. And it happens to be a local max. But this guy's a local max, and it is most definitely not the absolute max. It's not the largest value the function takes on, period. Similarly, this is a local min, but it's not the smallest value the function takes on, period. The smallest, the least value actually happens right here. And that happens to be not be a local min or a local max. It's not a critical point. But for functions of one variable, it turns out if you're looking on an interval, on a closed bounded interval, the absolute max and min values of the function occur on that interval. And they either happen at critical points, such as the case up here, or on the boundary, such as the case for the absolute min right here. So if we're not just looking on a boundary, it could be that there is no global max or no global min, or perhaps neither. So for instance, just like the function, for the function, say, f of x equals x, right? You just get straight line of slope 1. And if you don't restrict the values of x you're looking at, there's actually no smallest value, no absolute min, and no largest value, no absolute max that the function takes on from negative infinity to positive infinity. But if you restrict yourself to some closed bounded interval, we get both an absolute min and an absolute max. Okay, so all right. So I'm not going to dwell too much on this theorem. Yes, they can. So for instance, in this case, this is both a local max and a global max, an absolute max. But in this case, this guy's a local min, but not a global min. And this is a global min, but not a local min. So you can be one, either, or both. Yeah. Okay. So for functions of two variables, we have something similar. Let me write down our theorem here. Oh, shoot. So if we have a function of two variables and it's continuous, we're always going to deal with continuous functions in this class. It's continuous function on a closed. So these are two technical things we need. We need to be on a closed and bounded set. And I'll talk about what that means in a sec, but it's not something you're going to need to worry about too much. So if a set is closed, so if the boundary, or sorry, not the boundary, if the domain of the function or the domain we're looking at is closed, that means it contains all its boundary points. And bounded, we need the domain to be bounded. In other words, it doesn't go off to infinity. In other words, you can contain it inside some disk. But I'll just use doesn't go off to infinity. Not a technical term, but I think everyone knows what I mean when I say that. Right, it's bounded, right? You can contain it inside some disk. So as long as we restrict our attention to some closed and bounded domain. And what I mean by closed is, so for instance, like a disk, say like the unit disk, which contains the outer boundary circle. So like this boundary circle is the boundary of this disk here. If I remove one of the points, now it's missing a boundary point and it's no longer closed. But if it contains all of the boundary points, then it's a closed set. And the reason we need that is because it could turn out that the max or the min of the function actually occurs at one of the boundary points. And if that boundary point is missing, then we can't say anything about a max or a min. Okay, so we have a function of two variables on a closed bounded set. Then it turns out that that function obtains a max and a min, an absolute max and a absolute min value on that domain D. So F takes on. So that means we can find 2 points inside of D, point 1 and point 2. At point 1, the value of the function is the smallest it is anywhere in D. And at point 2, the value of the function is the largest it is anywhere in D. So it takes on a max and a min value in D. And it turns out that the only places the max and min can happen are at critical points in the interior of D. Interior just means not on the boundary. Or at points on the boundary. Those are the only places the max and min can happen. So in a closed bounded set, a function of two variables is going to take on max and min values. And those max and min values always happen either at critical points in the interior or somewhere on the boundary. And so that tells us, that gives us an idea how we're going to find the max and min values on a closed bounded set. So with that in mind, let's look at the process. I can, but really like, this theorem's not the super important thing. The important thing is like the process for finding max and min. Yeah. Oops. So how to find absolute max and min of a function of two variables on a closed bounded set D. Okay. So it involves basically three steps. So step one is we need to find the critical points, which lie inside of D. And I want to emphasize, they need to lie in D. So we're going to give you some domain we want to maximize and minimize a function on. So we don't care what happens outside of this area, right? So if I give you some triangular region here and a function, and that function happens to have a critical point out here, don't care about it. That can't possibly be a place where a local max or where a max or min could happen in D, because that lies outside D. So if you find a critical point, you need to make sure it's in your domain D. If it's not, we don't consider it. So I want to emphasize that. So basically what we're going to do is we're going to get a list of points, and at the end we're going to check the function and see what the max is and the min is at each of those points. So global, it's global in the little world we're talking about in D, right? So global doesn't necessarily mean all of R2. It means everywhere we're considering. Yeah. So maybe it's a slightly confusing thing, but yeah, it's like, this is the world we're considering. Yeah. Okay, so we find the critical points in D. That's going to be some set of points. Write those down. 2, you know what, let me just do this. And we're going to evaluate the function at each of these critical points. We're just going to get a list of values here. So we got a few values there. We'll come back to them in a sec. Step 2 is we're going to find the max and min values of our function on the boundary. So there's a lot that goes into this. This is sort of the new thing. But this is broadly what we're doing. We're going to break this down into a few pieces, and we'll see a new way of doing this, in fact, tomorrow, when we talk about Lagrange multipliers. But this is what we're going to be doing here. So part A, so the boundary is generally going to consist of a few pieces, right? We're not going to be able to usually what's going to happen is you're going to have like a square, a rectangle. And in this case, we look at each side of the rectangle because we can write each piece as just a single function, right? So say like this guy here, this will be one piece. And this piece is right here, given by y equals 0. That line there. This guy is going to be x equals 0. This is going to be, say, y equals 1. And this is going to be, say, x equals 1. But each piece of the boundary you're going to write as the graph of some function. So we're not going to be able to write the entire boundary using a single function. They're going to be at least two. And those two pieces are going to come together. Those two plus pieces are going to come together. And where they meet, we get corner points, right? So what we're going to do is we're going to check f at each corner point. I'm going to put corner in scare quotes here because sometimes it's what we would normally refer to as a corner, sort of a sharp edge there. But sometimes if we have, say, a disk like this, there are no obvious corners here. But what we're going to do is we're going to say, okay, the top piece, y equals square root 1 minus x squared, is going to be one piece of the boundary. And the bottom piece, y equals negative square root 1 minus x squared, is going to be another piece of the boundary. And where those two come together, right here and right here, those are the corners in this case. It's just where the pieces of the boundary come together. So we're going to check f at the corners. And then for each piece of the boundary, what we're going to do is we're going to rewrite our function as a function of one variable. We'll see how to do that. So we're going to rewrite it as a function, we'll call it f bar. Of one variable. So our function, we're going to transform it into a new function on each boundary piece. And then we're going to find the critical points of this new function of one variable. So we're going to evaluate our new function, f bar, at the critical points. Of f bar, the new function on the boundary. And we'll see how we do this. So for the boundary, we're going to check the corners. And then for each piece of the boundary, we're going to get a new function. We're going to find the critical points of that new function. And then we're going to check our new function at those critical points. So now we have some more values. So part 3, we just go back to 1 and 2, the critical points. We check the values at the critical points. And then on the boundary, basically we found the max and min on the boundary. So the largest value from this list so the largest value from steps 1 and 2 is going to be the max. And the smallest value from steps 1 and 2 is going to be the min of our function. Sure. So we have our function. We have our closed bounded set D. Step 1, find your critical points, which lie inside the region we're considering. Check your function there. Easy. Step 2, split the boundary into pieces, where each piece you can write as the graph of a single function of one variable. It's a curve. We're going to transform our original function into a new function. We'll see how. Find the critical points of that guy and look at the value of the new function there. So now we have a list of points. The biggest value from that list is the max, the smallest value is the min. Okay, so step 2 is kind of the lengthy, difficult, new thing we're doing. So let's do a couple examples. All right. So let's find the extreme values of the function uh, 2x plus y minus 3xy on the square, which is the set of points x, y, where x and y both lie between 0 and 1. Whoops. So the unit square. X goes from 0 to 1, y goes from 0 to 1. That's our domain D. Okay, so first thing you always want to do with these problems is, whoops, draw a picture of your domain. Even if it's really simple, just draw a picture of it. It'll help. Okay, so our region D, x goes from 0 to 1, y goes from 0 to 1. We're looking at everything inside of this square. That's our region D. Okay, so we're going to break up the boundary into pieces, and we're going to label them just to make it easy to keep up with, and also to make the grader's life easier when you take an exam. So let's say the left piece is 1, the top piece of the boundary is 2, or sorry, left side is 1, top side is 2, right side is 3, bottom side is 4. Those are the 4 pieces of the boundary.
I just had a quick question.
Mm-hmm.
So, like, I see how it says like y is less than or equal to 1. So I know how you get that boundary, but how do you know that x ends at 1? All it says is like x is greater.
So what this means is, so it means x and, so this is maybe confusingly written, but it means x and y are both between 0 and 1. So maybe a better way to write this would be to say x goes from 0 to 1 and y also goes from 0 to 1.
Okay.
Yeah.
Gotcha.
Clarify that? Yeah.
Yeah, thank you.
Okay. So step 1, we're going to find the critical points in D. Okay. So critical point of our function, remember we set both partial derivatives equal to 0 and find the points which satisfy both of these. Okay, so in the interest of time, I'm going to go quickly. So the partial with respect to x of our function, 2x becomes 2, y becomes 0, minus 3xy becomes minus 3y. Set it equal to 0. And then do the same for the partial with respect to y. Partial with respect to y, 2x becomes 0, y becomes 1, and minus 3xy becomes minus 3x. Okay, so when you're trying to find the critical points, you're going to have two equations, and either one of the equations is going to give you a definite value or a definite set of values for a single variable, or you're going to get a relationship between the two variables. We're lucky here, and both of these just give us definite values for each variable, so this is very easy. The first one tells us what about x or y?
Y equals 2/3.
Right, so the first one says y is equal to 2/3 at a critical point, and the second one similarly says x is equal to 1/3 at a critical point. So there's only one critical point. And that is the point 1/3, 2/3. My goodness. So that is our one critical point. First thing we need to check, is this inside of our domain D? Because if it's not, we're not even going to check the value of the function there. We're just going to throw it out. But is this in D? Does x lie between 0 and 1? Y lie between 0 and 1? Yes. It's in D, so we're going to check our function there. So f of 1/3, 2/3 is going to be 2 times 1/3 plus 2/3 y minus 3 times 1/3, which is 1, times 2/3, which is just 2/3. The value of your function at our critical point, our only critical point, is 2/3. Circle it so you know where it is. We'll come back to it later. Just going to add that to a list, and then we're going to see what's the biggest number from that list, what's the smallest number from that list. But we're done with that for now. Okay. So step 2. we're going to check the boundary. Okay, so part A, we just find the corners. So however we define the pieces of the boundary, it's very easy for a square. It's just each side is a piece. Wherever those pieces come together, those are the boundary points. We need to check our function at each of these boundary points. So what are our boundary points? Well, we have 0, 0, 1, 0, 1, 1, 0, 1. So let's just check our function at each of these. F of 0, 0 is, of course, just going to be 0. Add that to the list. F of 1, 0 is going to be 2 plus 0 minus 0, so 2. F of 0, 1 is going to be 1. And F of 1, 1 is going to be 2 plus 1 minus 3, 0. So we add those to our list, and then we forget about them. We move on. Okay. Now we deal with each boundary piece separately. Now here's the new bit. So I'll do the first boundary piece sort of in depth, and then we'll go a little quicker on the other ones. But here's what we do. You write the equation of each boundary piece. So each boundary piece, it's going to be some curve. And we're going to write this curve as the graph of a function of one variable. Right, so, okay. Piece 1, the left half. What do all of these points have in common? So they lie on what line? X equals 0. So they lie on the line x equals 0. So it's x equals 0. So every point on here are going to be x is equal to 0, y is equal to whatever. So every point on here is of the form 0, y. But we're not considering all such points. We're only considering the points where y goes from 0 to 1. Does everyone understand that point? Now what we're going to do is we're going to turn our function to 2 variables into a function of 1 variable, and now it's going to be a function of 1 variable on an interval. And we find the critical points of that function. Okay. So instead of f of xy, now our new function, f bar, let me call it f bar 1 because it's on side 1. It's only going to involve y, as we'll see. But what we're going to do is we're going to take our original function and we're going to plug in the points on this guy, 0, y. So we're going to plug in x for 0, y for y, and we get 0 plus y minus 0. So that's our transform function on the left piece of the boundary. So now, we know the max and min of this function on the interval, y goes from 0 to 1, can only happen on the boundary, the edges, so where y equals 0 or y equals 1, or at a critical point on the interval. So what we do is we find the critical points. So we take the derivative with respect to y. So what's the derivative of the function y?
Is that just f of y, and then you said is equal to f0 comma y is equal to
So
y?
it's f bar, just to differentiate it. So it's
F
f bar
bar?
sub 1, because we're going to have 4 different functions on each.
Oh, okay. Sorry. Okay.
So we take the derivative of this. Well, it's just 1. Don't worry about the fact that it's y. It's just a function of one variable now, and take the derivative with respect to that function. So this is never equal to 0. So this has no critical points, so we have nothing to check. Okay, so I want to clarify a point. So I said the max and min could happen at critical points on the interval or on the boundary. But we didn't check the boundary. We're only checking the critical points. Well, it turns out we've already checked the boundary. The boundary are always going to happen where these pieces meet. And those are just the corner points. And that's why we checked those already. Because if you check the boundary, y equals 0, y equals 1, if you do that for each piece, you're double counting all the corner points. So just check the corner points, and then that gets all the boundary points out of the way. And then you just need to find the critical points on each piece of the boundary.
So do we take the derivative with respect to y to find that no critical point there?
Right. So we have a new function. We forget about the old one. And we take the derivative of that new function and set it equal to 0. Wherever that happens, that's a critical point. You also need to make sure that that happens inside the region you're considering, where y goes from 0 to 1. So if we happen to, say, get y equals 2 as a critical point, we wouldn't consider that because that's outside of our guy. But that's generally not going to happen too much. Okay, so there are no critical points on this left boundary piece.
I'm sorry, and that's because of the domain, correct? Because we're looking, because of the 1 from our domain, it's from 0 to 1 of y.
No. So in this case, there are no critical points because a critical point of a function of one variable is just where the derivative is equal to 0. The derivative is, let me emphasize that, the derivative is never equal to 0 here. So that means there are no critical points.
Right, yeah. I'm just saying when we took that derivative, it's with respect to y because of the domain given at the beginning. Like,
yeah, we turn our original function now into a function of just one variable. And then you take the derivative with respect to whatever that variable is. Yeah. If that makes sense. We'll do some more, and then hopefully this will make more sense as we do some more. Okay, so then let's check the other very quickly. Boundary pieces. So the second is the top boundary. Okay, what are all the points on the top boundary? So that is a piece of what line? Y equals 1, right? So the top guy comes from the line y equals 1. And so the points on there are going to be x is whatever, y is equal to 1. So basically, you look at the equation of whatever curve you have, and that'll tell you what you're subbing in for one of the variables. And then the other variable is just going to be itself. So all points on this guy are the form x, y is equal to 1. And then x lies between x equals 0 and x equals 1. So now what we're going to do is we're going to, let me write it this way. We're going to take our original function and we're going to plug in the points x1 into it. So x is equal to x, y is equal to 1. And that's going to be our new function. And it's only going to involve x. So our new function f bar sub 2. So f of xy, 2x plus y minus 3xy, plugging in x equals x, y equals 1, we get 2x plus 1 minus 3x times 1. So 2x plus 1 is now y minus 3x times 1. So we get 1 minus x as our function on the top boundary. Okay, so we're going to find the critical points of this by taking the derivative. The derivative of 1 minus x is just -1, never equal to 0. So we get no critical points. So no values to check. Okay, so 3 and 4 are going to work largely the same way. I'm going to blow through them really quickly. So 3 is the right side. So that lies on the line x equals 1. So all the points on there are of the form x is equal to 1, y is equal to itself. Y lies between 0 and 1. So plugging in x equals 1, y equals y into our function, we get our new function. So that is 2 times 1, so 2, plus y, minus 3 times 1 times y. So 2 plus y minus 3y. So 2 minus 2y. Is our new function. Take the derivative, we see it's -2, no critical points. Let me just circle that. And would it surprise you to learn, on 3, doing the same process, we get no critical points. I'm going to skip the process because it's exactly the same as the other ones. Okay, so now we take all the values we found from steps 1 and 2. So in step 1, we got the value 2/3. So this is step 3. We're going to compile our list. So we got 2/3 from step 1. From the corners, we got 0, 2, 1, 0. You can write 0 twice, doesn't matter. And then from part B, where we found the critical points on the boundary pieces, we got nothing from any of those. So nothing else on those. So now we have a list of several numbers. The biggest number is the max, the smallest is the min. So our max is 2. And our min is 0.
And we got these from plugging it in, correct? Into these equations right here.
Yeah. Yes. The 0, 1, and 2 came from the corners. When we check the corners of the boundary, at 0, 0, we got 0. At 1, 0, we got 2. At 0, 1, we got 1. And at 1, 1, we got 0. Yeah. Okay. Thought I would have more time. I really wanted to do another example. So let's just say, okay, so if you need to go ahead and go. My apologies. I wanted to do another example. But if you still have time, or if you want to come back and look at this later, I think it's really good to do a more complicated example where something actually happens on the boundary, where you can find critical points. So we're going to do an example like that real quick. So the max and the min are going to be values of a function. So if they just say, what are the max and min of this function, you're just going to get numbers. Sometimes they want points. So like they could say, like, what are the dimensions of this box or whatever, which maximizes the volume. And then sometimes you need to keep track of that. But usually we can just forget about the points and just find the max and min values. But it depends on what the question is asking, if that makes sense.
Just to go over this again, where did we get like the 2/3 from? Like, right, the 1 and 0 are the corners from the domain.
So the 2/3 was from so we need to find the critical point of our original function of two variables, which lies inside D. So that was from the critical point. The critical point was at 1/3, 2/3.
Yeah.
When we check our function at that point, we get the value 2/3.
Okay.
Yeah.
But we only use 2/3 just because it's y.
No. We use 2/3 because that's the value. That is f of 1/3, 2/3.
Oh, right.
Plugging in our critical point into our function, and it happened to be 2/3.
Okay.
Yeah. Yes. So yeah, what we're doing is we're finding these certain points. We're looking at our function on those. We're adding those to some list, and then we're finding the biggest number on that list and the smallest number on that list. If you need to keep track of the points, then you should be doing that. But I mean, you could always go back in your work and find those points. But usually we just care about the values of the function. Okay, so I'm going to do one more example. Should be relatively quick. So let's find the max and min value of the function x times y on the unit circle. So the set of points x, y such that x squared plus y squared is less than or equal to 1. Okay. So first step, step 0, just draw your domain. Just draw it. It'll help you think about the problem a little bit. So this is just a unit circle, or it's the unit disk, everything inside the unit circle. Also counting the unit circle. So we have a unit circle and everything inside. That's going to be D. Okay, so our boundary is going to be this boundary circle, which, looking at it, there are no obvious corners, right? No sharp edges. But what we're going to do is we're going to break this up into two pieces. The top piece is going to be the piece of y equals square root 1 minus x squared. So the reason we do that is you can write the entire thing as x squared plus y squared equals to 1. But what we want to do is we want to change our original function into a function of just one variable. And so we need to get one of the variables by itself. So in order to do that, we're going to have y is equal to square root 1 minus x squared for the top. And for the bottom, that piece is going to be y equals negative square root 1 minus x squared. And where the two pieces come together, those are going to be the boundary points. That's going to be the point 1, 0 and the point negative 1, 0. So that's how we're going to do the boundary. Okay, step 1. We need to find the critical points of our function f. So we take both partials, set them equal to 0. So the partial with respect to x is just y. Set that equal to 0. Partial with respect to y is just x. Set that equal to 0. Boy, that makes life easy. What are our critical points?
Isn't it just 0, 0?
Right. So the first equation tells us y has to be 0. The second tells us x has to be 0. There's only one such point satisfying both of those, and that is the point 0, 0.
And they're in our domain as well. So I think
Yes,
we're good.
you do need to check that, get in the habit. So 0, 0 is clearly in this domain. It's just the center of our disk. Yes, that's a good point. Always get in the habit of checking that that's in D. And then we check the value of our function here. Well, it's 0 times 0, which is 0. And we will add that to our list. So that takes care of the critical points. So now let's check our boundary. So first thing we check are the corner points where the pieces of our boundary come together. Well, the way we divided up the boundary, the corner points are 1, 0 and negative 1, 0. So let's check f there. Well, f at 1, 0 is going to be 1 times 0, which is 0. Add that to our list. F of negative 1, 0, it's going to be also 0. Add that to our list. Now we're going to transform our function on each piece of the boundary, find the critical points on of that transform function, and then check the value of the transform function at those critical points. Okay, so our first piece, the top piece of our boundary, we'll call that Roman numeral 1. So we said that is a piece of the function. Sorry, the piece of the curve y equals square root 1 minus x squared. And so all the points on there, if y is equal to square root 1 minus x squared, well, x is equal to itself, x, y is equal to square root 1 minus x squared. And x is going to go from what to what?
Couldn't that be negative 1 to 1?
Right. So we go from this leftmost point where x is equal to negative 1 to this rightmost point where x is equal to positive 1. So the points we're dealing with, the points we're going to plug into our original function are x is equal to x, y is equal to square root 1 minus x squared. So we're plugging those into our original function. And we're going to call this f bar 1. And it's just going to involve x. So wherever we see x in our original function, we plug in x. Wherever we see y, we plug in square root 1 minus x squared. This is our new function. We're going to forget about the old one. We're going to look at this function from x goes from -1 up to +1. We need to find the critical points of this function now of one variable between x at -1 and 1. So we take the derivative and we set it equal to 0. So the derivative of this, we're going to need to use the product rule. So it's x times square root 1 minus x squared. So first and then second. So derivative of the first times the second, 1 times square root 1 minus x squared, plus first times the derivative of the second, which is -2x over square root 1 minus x squared times 2, using the chain rule. And so that is, hang on, let me give myself some more room here. Square root 1 minus x squared plus x times -x, so minus x squared over square root 1 minus x squared. And then I'm going to simplify this to make my life easier. I'm going to multiply top and bottom of both of these terms by square root 1 minus x squared. Or sorry, the top and bottom of the first term. So we get 1 minus x squared minus x squared. So 1 minus 2x squared over square root 1 minus x squared. Set it equal to 0. Okay, so the critical points are also, okay, so it's where the derivative is equal to 0 and also where it doesn't exist. Well, the derivative doesn't exist where the denominator is 0, and that happens at x equals -1 and +1. That corresponds to the boundary points, so we don't need to check that. We've already checked that. So we just need to see where the numerator is equal to 0. That's where our derivative is equal to 0. So 1 minus 2x squared is equal to 0. So that means 2x squared equals 1. X squared equals 1/2.
So why wouldn't we need to check -1 and 1 again?
So we've already checked the boundary points. You could go ahead and plug those into your function. You're going to get 0 because those correspond to these points here.
Oh, what we did in the corner, just
Yeah.
in part A. Yeah.
You
Okay.
could, but I'm just telling you now, we've already checked them. And so you can save yourself a bit of time. So we get x is equal to plus or minus square root 1/2. Okay. Just to emphasize, critical points of our transform function, they're at 1 over root 2, -1 over root 2. And so what we do is we plug those into our transform function. So just a reminder, our transform function was x times square root 1 minus x squared. So plugging in our critical points, 1 over root 2, we get 1 over root 2 times the square root 1 minus 1 over root 2 squared. So 1 minus 1/2, square root of 1/2. So we get square root 1/2 times square root 1/2 is just 1/2. That's the value of our transform function at one of the critical points on the boundary. And then at the other one, whoops, sorry, no, we already did that. At the other point, where x is negative 1 over root 2, when we do that, we get negative 1/2. Okay, so that's the first piece of the boundary, the top part. The bottom part's going to work exactly the same. So I'll just rush through it. So that is going to be piece of y equals negative square root 1 minus x squared. So our points on there are going to be the form x, y is equal to negative 1 minus x squared. And here x is going to go again from negative 1 to 1. So now we plug those points into our original function to transform it. We're going to call that f bar sub 2. And that's going to be now x times negative square root 1 minus x squared, xy becomes that. We get negative x times square root 1 minus x squared. And the critical points are going to be exactly the same as the critical points of the original function, because it's just negative the original function, right? If you do negative of a function and you take the derivative, you get negative the derivative of the function. You set it equal to 0, though, that's going to happen at the same points because it's just negative the original function. So doing the same process, we get that this new function has critical points at plus or minus 1 over root 2. And when we plug those into this transform function, we get the same thing. Oops, we get plus or minus 1/2.
Oh, so our critical points for the previous one where we did square root of 1 minus x squared was actually plus or minus 1 over square root 2 and not negative 1 and 1.
Wait, what was negative 1 and 1?
Okay, so we in the previous slide, I think, yeah, we called we were doing the top piece and we found the derivative of f numerical number 1 x, and we said the critical points were negative 1, 1, and 0, and then you said that.
Oh yeah. So well, if you plug in negative 1 into the original function, you get negative 1 times square root 1 minus 1, so we get 0, and then same thing as 1.
Right, but if you plug in negative 1 and 1 into the original equation where we said, right, shouldn't that just be 0? Because 1 minus negative 1 squared is 0.
They are, but remember I said those correspond to the boundary?
Right.
Pieces, and on the corners, And at the corners we checked and we got 0.
Exactly. And
that's,
then
that's what we got there. It's okay if you double count the corners if you do them. If you want to be thorough. You can
Okay.
do that. It's all it's going to do is take a little more time on your part.
okay. Yeah, sorry.
If you've got the time.
I just got lost at where we found x is equal to 1 over the square root of 2 and negative 1 over square root of 2. Could you?
Okay, so what we do is, so you understand where we get this function from, right?
Right,
This,
we took the
x times
derivative.
square root 1 minus x squared.
Yeah, so we found the derivative. That's the 1 minus 2x squared over the square root of 1 minus x squared. Yeah,
And we
perfect.
find the critical points are going to be where that derivative is equal to either 0 or does not exist. So it doesn't exist where the denominator is 0, and that's x is plus or minus 1.
Exactly. Okay.
You can check that, and you see those both correspond to
Right.
The original function is 0. Or where the numerator is equal to 0, that's where the derivative is equal to 0.
Okay.
So at 1 minus 2x squared equals 0, you find x is plus or minus 1 over root 2.
Oh, that's what okay, that's why. Okay. I said 0 for some reason, but it's actually plus or minus square root of 1/2.
Yep, exactly.
Oh, okay. There we go. Perfect. And then that's perfect. Thank you.
Yep. And then the bottom piece works exactly the same way.
All right. All right. I was like, we had 0, and I was like, wait, how do we get 1 over square root of 2?
Yeah, yeah. Yeah, there's a lot going on here. So you kind of have to familiarize yourself with the process. And then once you do, you'll be able to follow along easier. It'll be easier to do. But like the first time you're seeing it, it looks like there's kind of a lot going on. Okay, so step 3, we find all the values from steps 1 and 2. From step 1, we only got 1 point and 1 value, and that was 0. Step 2, we check the corners. We got 0 and 0 at each corner. I mean, you don't have to list 0 3 times, but whatever. And then when we check the critical points on each boundary piece, for each of those, we got plus or minus 1/2. And I'll just, put that again from each. So just so we know where everything's coming from, that's from the corners. That's from the critical point of our original function in D. That's from boundary 1, and that's from boundary 2. So we have a list of numbers. Smallest is the min, largest is the max. So our max is 1/2. Our min is negative 1/2. Okay. Any other questions about this? Because a lot going on with there. That's why I wanted to do another example. Okay. Well, sorry for keeping you over again. So tomorrow we're going to be talking about Lagrange multipliers, and yeah, I'll see you tomorrow. Have a great day. Later, guys.
Hello, it's Claire.
Hi.
You haven't graded my exam yet?
Yes, I need to grade that. I'm going to grade it tonight.
Okay, I was just wondering if you
Totally forgot.
Okay.
But yeah, I'm gonna do that tonight. My apologies.
Thank you.
All right. Later.